This is Composite Materials lecture number 6. Sorry, it has been a little slow going here, but I hope to complete a couple more lectures in the next 2 days. Okay, so I would like to bring up homework number 5. I think it is number 5 or it could be number 4. I don't remember, but it is the next one. So what I want to bring to your attention, so after this class, I would like you to go and look up some references that describe general relationships between porosity and mechanical properties. You know that there are most of the time, if there is a porosity, it reduces the mechanical properties. But in some cases, it may be actually be desirable to have some kind of porosity in order to have toughness introduced into the composite material. And um, I would also like you to look up uh, what effect the processing conditions could have on porosity. And like for example, in the case of ceramic composites, you would like to avoid the porosity as best as you can. And so how can you avoid those problems with porosity, say in the case of a polymer matrix composite or in the case of carbon-carbon composites? I would like you to look it up just out of curiosity. Okay, so I would like you to understand that. So, talking about alumina fiber, aluminum composites. Now, most of these composites have properties in that are different in different directions. They are not isotropic in nature, like metals are, or metals or alloys are. So you can see that in the axial direction, because the fibers are mostly in that direction, you are going to get a higher elastic modulus or stiffness when the percentage volume fraction of fibers goes up. So you can see that no, 60% is probably the maximum, especially for continuous fiber reinforced composite, that you can have. So you can see that you can have as much as 100% or more increase in elastic stiffness when you go from 20% to 60%. You can also find that the tensile strength of these composites goes up quite drastically when you increase the fiber volume fraction. That's mainly in the axial direction, but in the transverse direction, it is not that effective because now you are actually testing the properties of the matrix rather than the properties of the fiber. Now, there is also a difference in properties compared to whether the fibers are continuous, viscous, or particle. In the case of particle, you are not going to get as much of an improvement when you increase the fiber volume fraction um, as is the case of continuous fibers. And that's because continuous fibers means there is less chance for the fibers to break and less chance for, so there is more chance for fibers to be holding the broken parts together. So the effect of continuous fibers is much better than in the case of particle or viscous. So if you had metal matrix composites, there are two ways of strengthening that you can have. One is direct strengthening, where you can have low transfer from the matrix to high modulus reinforcement fibers or particles. You can also have indirect strengthening, where the reinforcement induced changes in the matrix microstructure and properties. For example, if there are CTE mismatches, so you can have a shrinkage of the matrix around the fibers that can improve the fiber to matrix bonding. Or you can also have accelerated aging processes due to some nucleations at dislocations in the case of metal matrix composites. But this won't be the case in polymer matrix composites or ceramic matrix composites. So you can have silicon carbide fibers in an aluminum alloy matrix. The interesting thing is that these fibers are pretty large, so the effect of strengthening due to the fiber reinforcement may not be as apparent. So this is another picture of that. You can see that there is actually some small cracking between the fibers in the matrix because of the differences in CT between the matrix and the fibers. So the matrix is actually can shrink and expand much more than the fibers because the fibers are a ceramic fiber, whereas the matrix is a metal one. So that can cause cracks and actually reduce the properties compared to uh, the matrix by itself. So you can actually calculate the thermal stresses. There is a thermal mismatch where alpha m minus alpha matrix minus alpha of fiber, and so there is a thermal strain is actually this factor times the temperature difference. So thermal stress can be given as a function of elastic constituents times this thermal strain times a factor for geometry. So there are many, much research has already been done in these things. So if you are interested, you can take a look at that. If you take a look at tungsten copper system, where you are reinforcing a copper matrix with tungsten filaments, this is actually a model system. There is no chemical interaction at the interface, and there is a chemical etchant for delineating dislocations in a copper single crystal. There is a large delta T during the processing. Now, you may ask me, why can't we have copper fibers in a tungsten matrix? Just think about it. Copper melts at what? Um, what is the temperature at which it melts? It's much, much lower compared to tungsten, which melts at around 1860 or something like that. And copper uh, is probably 800 something. I forgot exactly, but that's probably what it is. So there is a tremendous change in temperature, melting temperatures between the two materials. So you can only have tungsten fiber reinforcement of copper rather than the other way around. So there is a large delta T during the processing, and therefore a large change in the expansion coefficients, and it can actually deform the matrix plastically. So you can actually have edge pits around the fibers. So in the case of aluminum alloys, you can have precipitation hardening. In the case of tungsten carbide cobalt, it can do other things. So you can actually see that there is an increase with respect to the percentage of tungsten carbide. So that is another composite system. So these are different kinds of metal matrix composites used in different applications. So if you had alumina with carbon short fibers, you have 12% alumina for wear and 9% carbon for lubricity. So it can be integrally cast with aluminum silicon engine blocks. It gives you 50% the weight of cast iron, but it has fantastic wear resistance compared to this. So this one, I believe it is the Honda Prelude, and I think this is also the same kind of material that is used in Honda NX. So this is a cross section, a microstructural cross section of this particular material. So you can have um, this composite integrally cast with the engine block, and it gives you tremendous wear resistance compared to those materials. You can also have metal matrix composites used in electronic packaging, where you can have silicon carbide fibers in aluminum matrix. So this is a composite material that is um, used for thermal management, and the advantage is that you can actually use this for thermal management of either silicon wafer or silicon carbide wafers. So you can see that the by increasing the silicon carbide volume loading, you can actually decrease the CTE to almost close to that of silicon itself. You can see that aluminum has almost 27 inch per inch in thermal expansion. By increasing the silicon carbide volume loading, you can actually decrease the thermal expansion coefficient, and it will also increase the thermal conductivity. So you are actually hitting two stone. I mean, um, you are killing two birds with one stone in this case. So these are all the variety of MMC systems, and you have the matrix in the case of aluminum. You have different kinds of reinforcements, and the advantages are given there. So you can also have some of these materials used for connecting rods and things like that. So if it is an aluminum metal matrix composite, you can see the uh, weight gains. So you can save as much as 60% weight with respect to a forged steel connecting rod. And it has almost, I mean, it won't have the same properties, but it will meet the needs of the application. So the only requirement is that it needs to have a fatigue strength of 210 megapascals at 150 degrees centigrade. And it has been estimated that 13% weight savings gives you more than 10% fuel economy. Now, with all this, why aren't more manufacturers, car manufacturers, automobile manufacturers not using these kinds of applications? Mainly the cost and the cost of proving this application rather than anything else. You can also have alumina fiber aluminum composite. I think, and it is made by squeeze casting. So mainly in the ring area is where you have this composite. So it gives you tremendous wear resistance at that area. So these pistons don't wear out at all. Now, let me go to something slightly different. We have been talking about composites. Let me describe something slightly different that I worked on in my previous career. One big problem with many of these composites is the cost of fabrication, cost of materials and cost of fabrication, especially ceramic materials composites. And the fact that you cannot get really, almost better than 80-90% densification for these composite materials. So you're going to have issues with the final applications. So we developed, actually not us, um, there was a researcher in DARPA called Bill Koblenz who developed something called fibrous monolith materials. So he took two ceramic powders and made them into a composite behavior. So they are not ceramic fiber or fiber reinforced composites. They are monolithic ceramics with a fibrous or woody texture, and they still exhibit graceful composite failure and high fracture energies. And it can actually be fabricated from low cost powders, and it can even be 3D printed. So that's one big advantage with these materials. And so this is a schematic of that material. So you have a strong ceramic surrounded by a weak ceramic material. So for example, this is the inside is diamond, which is polycrystalline, and it is about 200 microns, and you have tungsten carbide or tungsten carbide cobalt metal in the cell boundary. So this cell boundary is weaker, and it has got a tremendous ability to absorb the energy compared to the diamond itself. So you extrude this one time from starting from a cell made out of the strong material and the outer material made out of the weak material. You extrude that one time, you have these small fibers, then you bunch them up together and you extrude them again, and you get smaller and smaller and smaller fiber sizes. So you may start with something like 50 to 200 microns, and then you end up with something like 5 to 10 micron sized strong areas and about half a micron of weak area. The advantage is that if a crack is passing through this material, the weak material will deflect those cracks and the strong material will still hold together. So this actually becomes like a fiber reinforced structure. So you can have multi-filament extrusion. So this one is 500 microns. So each of these might be like 30 to 40 microns sized. And you can actually make it smaller and smaller and smaller. And one big advantage is that it has tremendous ability to act like a composite. It can take tremendous amount of impact energy, especially in the direction opposite to the fibers or transverse to the fibers. And it can be used in applications like metal cutting tools and drilling tools, etc. So that's one big advantage with these materials. And there is a company called Smith Tools International who is making these drill bits for drilling into the ground. And they are using these materials as the coating of the drill bits itself. So this is again another schematic of that. So this one shows a composite behavior. So you can see that the crack keeps on getting deflected by these cracks. And even though the overall strength goes down, it still maintains its composite behavior. So these are some of the big advantages. So you can have diesel injector nozzles. So if you have a material that can be burnt out, so you may end up with a very, very tiny filter, tiny sized filter using these materials. So let me show you this. So this one is each of these tool bits is covered with this soccer ball type of material, and each of this small circle, it's not exactly circular, but small black area is the actual diamond material, whereas the um, slightly less dark material is the tungsten carbide cobalt. And the advantage is that when it hits a hard material, when it is drilling through hard rock or hard earth, these edges get broken off, and it keeps getting sharpened by itself. So it is a self-sharpening composite material. And what we found is that um, these drill bits were not, were the same expense as the diamond drill bits that they were using previously, but it had something like 10 to 15 times more lifetime compared to the traditional diamond drill bits. So that is one big application of ceramic composites that you might find in popular literature. This is another example of metal matrix composites in track shoes. Um, you can have, so these spikes are made out of particle reinforced aluminum matrix composites. And there is another example of superconductors that are being used, um, from these materials. So you keep extruding them again and again to make really, really tiny fibers that are surrounded by um, a soft matrix material. Okay. So I'm not going to go too much into depth with that. So this is an example of that. Okay. One big advantage with metal matrix composites is that it is possible to recycle them, and um, or you can add virgin material to the composite scrap to obtain a new composite material, and you can reuse them again and again, unlike other types of composite materials. So I would like you to go through that and read through them. Not going to go too much into depth about it, but just um, interesting piece of information. Okay, so again, this is another manufacturing process for metal matrix composites. You can have the fibers go through a matrix slurry, impregnate it, and then stack it up and burn out the binder and hot press them into getting the final composite material in this form. So in this case, it's a ceramic composite with nickel-on fibers, which is silicon carbide fibers, in a glass matrix composite, which is a transverse section of that. So it is hot pressed to get the final composite material. Or you can also do a process called chemical vapor infiltration. So you take this fiber preform, you inject the gases in, you heat it up, and during the heating process, these gases will deposit a matrix around the fibers, and the spent gases are taken out through the top, and the other gases deposit the matrix around the fibers to get a solid matrix material. Or you can also do what is called, it's called polymer impregnation and pyrolysis. You laminate the fibers and then you impregnate that with a polymer, which is a precursor for the matrix. Then you burn out the binder, and then you sinter that. It shrinks, the matrix shrinks, the fibers don't shrink, and so you end up with something like 60-70% volume fraction of the composite material. So then you have to re-infiltrate that with the matrix in order to get the composite to 80-90%, 90-95% final densification. So this reimpregnation pyrolysis has to be done multiple times. Sometimes in the case of carbon-carbon composites, you have to do this something like 10-15 times. So that's one of the reasons why this is an expensive process. There is also another process called electrophoretic process. So you put that as an anode, as a cathode, and the anode will provide ions which will go and deposit around the fibers in the cathode, and then you end up with the final composite material. So this is a cross section of the composite made by electrophoresis. This process has not been around for a very long time, but it is used for many different applications. Now, switching gears slightly, maybe I will stop here and continue in the next section of this lecture.